Do you know what inductance is and why it matters in electrical engineering? Well, let's break it down. It all starts with a conductor, a material that allows electric current to flow through it. When this happens, a magnetic field is created around the conductor. Now, if the current changes, the magnetic field changes too, which induces a voltage across the conductor. This is what we call electromagnetic induction, and it's the foundation for understanding the concept of inductance. This induced voltage works to oppose the change in current, almost like it's trying to maintain a status quo. Inductance, represented by the symbol L, quantifies the conductor's ability to store energy in this magnetic field. It's measured in units called henries, named after Joseph Henry, an American scientist who discovered self-inductance independently of Faraday. So, in essence, inductance is the ability of a conductor to store energy in a magnetic field when an electric current is flowing through it. Now, let's dive a bit deeper and explore the first type of inductance, self-inductance. Imagine a single conductor or coil through which electric current is flowing. This current generates a magnetic field around the conductor. But here's the interesting part. If the current changes, the magnetic field changes too. This change in the magnetic field induces a voltage right across the conductor itself. This voltage, which we call self-induced electromotive force, or EMF, pushes back, opposing any change in the current. It's like the conductor saying, "Hey, I was comfortable with the old current. Why change?" But what determines the magnitude of this self-inductance, you ask? Several factors come into play here, including the shape and size of the coil, the number of turns it makes, and the material of the core around which it's wound. That's self-inductance for you, where the conductor itself experiences an induced voltage due to changes in its own magnetic field. Moving on, we have another type of inductance known as mutual inductance. This phenomenon comes into play when two or more conductors are in close proximity. As the current in one conductor changes, it generates a changing magnetic field. This change doesn't keep to itself, oh no. Instead, it reaches out and induces a voltage in its neighboring conductor. This is what we call a mutually induced electromotive force, or EMF. Now, the strength of this mutual inductance depends on a few key factors. The orientation of the conductors to each other and their distance apart can make a big difference. Just like with people, the closer and more aligned they are, the stronger the connection. Additionally, the individual inductance of each conductor also comes into play. So, to sum it up, in mutual inductance, it's all about how one conductor impacts another through their shared magnetic field. So, where do we see inductance at work in the real world? Well, let's dive right in. First up, inductors. These passive components are designed with specific inductance in mind and are typically coils of wire wound around a core. They're key in applications such as filtering, energy storage, and impedance matching in circuits. Next, we have transformers. These clever devices use the principle of electromagnetic induction and mutual inductance to transfer electrical energy between two or more coils, and importantly, they provide electrical isolation. Speaking of energy, let's talk about energy storage. Inductors can store energy in their magnetic field when a current is flowing through them. This capability is vital in various electronic circuits, including switching power supplies and energy harvesting devices. Then there are oscillators and resonance circuits. Here, inductance teams up with capacitance to form the basis of these circuits, which are used to generate and filter specific frequencies in communication systems, signal processing, and more. Last but not least, inductance plays a critical role in managing electromagnetic interference and ensuring electromagnetic compatibility in electronic systems. Inductors and transformers can be used to suppress or filter out unwanted signals and noise, improving the performance and reliability of electronic devices. From transformers to oscillators, inductance truly is at the heart of many electrical systems and devices. To wrap up, we've unearthed the essence of inductance, its unique ability to store energy in a magnetic field when current is present. We've broken down the concepts of self-inductance and mutual inductance, shedding light on how magnetic fields can induce voltage across conductors. Furthermore, we've explored the pivotal role of inductance in applications like inductors, transformers, energy storage, and oscillators, to name a few. Remember, Understanding inductance is key to grasping the behavior of many electrical components and systems. So, keep exploring and keep learning.